regression, generalized linear models. All these models and the models in the future, they can be fit into this framework. And the framework is designed to measure the out-of-sample performance in a very smart way. It's, try to make the best utilization of the data we have on hand. Right? So last time we talked about all these generalized linear models. Let me skip the review part. Right? So the plan for today is the first thing we need to go through is this important conceptual method called the validation. We are going to introduce 3 different validation methods, but at the end you will see it's basically one. Only the last one is the practical one. The first 2 we need to introduce them just for the sake of building up the idea of the last one. So at the end we'll all converge to the k-fold cross-validation. But let's do that one by one. And this is mostly conceptual, verbally describing how things should be done. And I guess we'll spend an hour on the conceptual part. But a lot of the things are easy said than done. And when we implement things in the coding part, you will see there are actually a lot of practical concerns and a lot of things, little details we need to be careful. Right? So we spend most of the time on the coding part. How do we implement this validation kind of idea? And towards the end, we'll talk about the model selection. That was the big question left unanswered when we talk about linear and the generalized linear models. We say there are so many predictors that can be potentially put into the model. How do we really choose this one should be in, this one should be out? And we didn't. We were not able to do that because we don't have a good way to compare the performance of the 2 models, the out-of-sample performance. Right? We have the in-sample measures, but that's not good enough. Right? And today, after having this validation kind of idea, we can use the validation tools to measure the out-of-sample performance of all these linear models. So eventually, we can have a simple framework helping us to choose the variables for our model. Right? And also, that's a general idea of whenever you are struggling on whether I should do the model this way or the model that way, or whether I should do this model or that model. Eventually, later you will see, whenever you have such a doubt, throw these models into this framework and let's do a horse race. So a lot of the human decisions can be delegated to this horse race kind of method. Let's just try which one performs better. Right? Given this validation kind of a method, they can tell us how they perform eventually out of sample. So with that thing, any possible model candidates can be put into that kind of environment, just run. Right? So that's a big picture. Right? So let's start it from the most important message. That's this picture of this whole course. Right? We talk about, in the first session, we talk about in-sample error and out-of-sample error. We say by increasing the model complexity, in-sample error can always go down, and eventually we should be able to find a way to reach a 0 error. But that doesn't say anything about the model performance out of the data set. And the out-of-sample error actually goes down and goes up. There's an underfitting area, there's an overfitting area, and there's somewhere we should be able to find the optimal fitting. Right? That's the optimal model or optimal model complexity. We have been trying to do that. We know we should focus on out-of-sample error, and we have been trying to do that in several special situations, like the mixture model. We have this homework last time. The mixture model, we say we can build a logistic regression, we can build a k-nearest neighbor, and we can evaluate these models, the out-of-sample performance by using another test data set. Right? Because that's a simulation, we can simulate more data points. We just need some separate data sets to evaluate these models. So we can do that when we have a test data set, basically another large enough data set. Right? But in most of the practical situation, this is too much luxury. You don't have another large data set for the sake of testing your model. You don't have that. If you have a large data set, why not use that for training? Right? Why do that? Right? So in practice, the amount of data is finite, versus in simulation, the amount of data is infinite. You say, give me another one, I can simulate another one. In practice, the amount of data is finite. We need to really think about how do we make best utilization of this finite data set, which ones to use to train our model, which one to use for other purpose, right? But there's some constraints out there. We cannot get arbitrarily many extra data sets as we want. So in order to overcome that, we said we have introduced some theoretical ways of doing that. We introduced adjusted R-square. That is a combination of the in-sample error and the model complexity. That's the number of predictors, right? So that's a number eventually gives you, that captures the two concerns, to have a good fit in sample and to have a generalizable or simple model that may be good out of sample, right? But the issue is there's no theoretical foundations why it works and why it not works, and also there are many, many candidates out there you can use. So we have been using AIC to do model selection, adjust R-square, all these things, right? So they are not really satisfactory. And today we are going to talk about a simple and kind of a universal framework that can help us directly estimate. So giving a model, I should be able to estimate the out-of-sample performance without having another data set. I'm just estimating the same thing with the given data set I have on hand, right? So that's a big thing because, yeah, in most of the situations, you don't have another data set. Right? So the idea of validation is not, let me go back to the, I want to highlight, we mentioned this a little bit, but we say in practice, there's a training data, there's a validation data, there's a test data. Right? So I think that the first class we mentioned a little bit about the difference. Right? We said training data, we should have the X and Y's. X are the training data is like a homework exercise, right? By doing this exercise, we are building the knowledge about the connection between X and Y. So we should be given X and Y, and we are looking at this X and Y and trying to figure out what the relationship, what's the kind of the function that connects the two, right? So today we're going to introduce validation data. And validation data is basically another data set with also some X and Y, and these are like a mock exam. So I want to know how well I have learned from the training data, and I have to give myself some simulated exam, right? So I said, yeah, this is a different data set, and I know the questions. I also have the answers. But let me pretend I don't know the answers. Let me work on the mock exam. I'm grading the performance of myself, my learning, right? That's the validation data. And the test data is the real exam. And in the real exam, you don't have the answer. You have the questions, you don't have the answer, right? So that's a situation. And depending on your context, so if this is an applied problem, you should have a big data set, and you need to decide how much the data you use for training, how much the data you use for validation to evaluate yourself. But after you have your model, you deploy your model to the real practice, then you are seeing new data, right? Think about the credit default. I'm building the model, and then I'm deploying that. So the test data is really the customer coming in the future. I don't really know who they are, how good they are. So I have to make a prediction based on this, their X, right? And if your context is like a data competition, typically you are given an initial data set to do whatever model you can. And there will be a test data set, but there's only X available. So your task is to predict the Y on the data set. And the competition organizer will compare your Y with the true Y and measure your performance. But at the end of the day, you don't really see the Y out there. And you cannot use this test data set to change your model or whatever. So that's not the reality, right? So the fundamental difference of this validation and test data set is validation data set, we have the answer. So we are trying to evaluate ourselves and find, are we learning the best day? Right? Test data set, we don't have the answer. And you cannot use the test data set to change your learning behavior, all these things, right? You don't really go to the exam and then go back and change the way you learn, right? That's not the thing, right? So basically, we have already covered the validation set approach. So the idea is I need to train models and need to evaluate the out-of-sample performance. And in order to evaluate the out-of-sample performance, I need another data set. But I don't have the data set, another one. So I basically split the data I have on hand into two parts. I use one part to do the training and use the other part to do the validation. Right? So that's a simple idea. But the keyword is here. We need to randomly divide the data. How to divide is a artistic question. Some people say 50-50, some people say 60-40, some people say 70-30. Right? But that's not a big issue out there. In order to divide that randomly, that sounds like a trivial thing. Later I'll show you how to do that. But in many situations, that's going to be quite difficult. Think about last time we talked about the credit default. There are like 10,000 customers. Out of 10,000, you have 300 bad guys, right? So you need to divide these 10,000 points into two parts. And hopefully you have bad guys in both sets, right? If you don't have bad guys in both sets, you're in deep trouble. You might, in a training data set with no bad guys, you say everybody is good. And then you evaluate your model is so bad, right? That's the issue, right? If there are only 3% of the bad guys and you are kind of randomly assigning, that may not always do the job, right? So in that situation, you might need to, just like the case control sampling, you may need to sample the good guys and bad guys separately. So let me take all the 300 bad guys, put it 50-50, and take the rest of the good guys 50-50. You may need to do something, but that's no longer random, right? That's no longer random. But that's about why. Sometimes you have an unbalanced why. That's an issue, but that's solvable. The more troublesome situations is about those X. You have some X, like you're predicting the amount of money people make. Then you have one X being the education background, for example. You have 80% of people having college degree, and there are 1% of people having PhD degree. How do you, when you randomly split the data, how do you make sure there's some PhD here, there's some PhD there? Right? It's just one column. In reality, you might have many columns. They're just categorical variables. They're just a bunch of categories. They're just too tiny. Right? You might have 20 categories, but the majority of people are in the 3 categories. There are a bunch of smaller categories. And when you split, you need to make sure that it at least exists in both sets. Otherwise, there's no way in your model, you don't even know the existence of such a type of people, right? It's not a trivial thing to do. And this is just splitting data into 2 parts. Later, we'll split the data into 10 parts and more issues. Yeah. So, but assume we can easily split the data into 2. Right? So with that we will use one part for training. So that's the so-called training data. We use the other part for validation. So that's the for evaluation or validate my model. Right? And hopefully we should have a model based on this half of the data. Then this becomes another data sample that we didn't use the information here to build our model. Right? So we can predict on these guys. We know the true Y. We can predict on their Y. So we can measure the error. Right? So this is the so-called validation error, the error we make in the validation data set. And the hope is this validation error we obtain should approximate the overall out-of-sample error. Right? That's the hope. And it doesn't always just perfectly just approximate the error, but at least that's one big step forward. In the past, we were evaluating our models using in-sample error. At least this is an error that is out of sample, right? So at least we are moving one step. So what else? And what are the issues? Let's try to do that, and you will see the issues. So this is the most natural way of thinking, right? I need a data set. I don't have another data set, so I just cut my current data set into two and do that separately. So let's do that. So this is a quick example. So let's not spend too much time on a data set. It's about data set about automobiles. Each row is one car model, right? And there's several features about these cars. Here, let's just make a simple example. We are trying to predict the mileage per gallon. So that's a fuel efficiency by using the horsepower of the engine, right? How much power the car can output versus how much fuel it consumes, right? So naturally, there should be a relationship. But the question is, what are the models we should choose? So you might just take an example. You might have 10 candidates for your model because you are not really sure how many order of polynomials we should include. Some people say it should be a linear relationship. Some people say it should be a quadratic. Some people say it should be up to the 10th order, right? So how do we decide? And we want to decide, make such a model selection based on the out-of-sample performance. Right? So what do? We just, according to the described method, we just split the data into two. Actually, that's not a big data set, about 400 points, 392. So we split that half-half randomly, 196 for training, 196 for validation. Okay? So what do we have? So what we need to do, we have 196 data points for training, so we need to train these 10 different models. We have 10 candidates. We need to choose the best. So there are 10 different models. So we train them, and we use these 10 models to predict on the validation data set. For each data point, there are 10 different predictions by these 10 models. Right? So we evaluate the errors. So after aggregating the errors, we end up having this plot. So these are the models. So we have 10. N goes from 1 to 10, and the vertical axis is the mean squared error. Right? So that's nice. This is no longer in sample. This is out of sample. This is another data set. So we have the mean squared error. Right? So how do we choose the best model here? 7? Where's 7? 7? Any different opinions? Huh? 10? What? Okay. Huh? 2? Who is going for 1? As long as we don't choose 1, we are safe, right? 1 is obviously a bad model. But all the way from 2 to 10 is hard to differentiate, right? So which one you choose is subjective. But in general, people choose 2 because they say they're roughly similar. And later we have a stronger reason. They're roughly similar according to this plot, and I would go for a simpler model because if I'm talking about a story, having second order is much easier than having 10th order, right? So I can talk about a story. It's actually a quadratic shape functions, all these things, right? In terms of a prediction, probably you would go for 7 if you're doing a data computation you want the model gives you the highest accuracy. If that's all you have, probably you should go for 7, right? Or yeah, but that's a subjective part. That's not what we are going to talk about. The real issue is this is one run of this validation kind of idea. We are splitting the data to 2 parts and evaluating these 10 models. If we repeat this whole thing 10 times, just repeating this randomly splitting the data and measuring the error for each of the model, each run we get 1 line. So we repeat that 10 times, we get 10 lines like this. Right? So what are the problems you see? Any problem? So there are a lot of variability, right? There are a lot of variability, and we hope to use these numbers as an approximation of the out-of-sample error. But sometimes it's like a 19, sometimes it's like a 24. How do we trust these numbers? And this is after you have run 10 times, right? Without running 10 times, how do you know to what extent I can trust this number, right? And that's not only about the number, it's about the selection. I have chosen number 2. If I happen to see, for example, the orange line, if I just run it once and I see the orange line, I'm going to take this guy. Right? If I see the yellow one, I'm taking this guy. If I see this guy, I'm taking this guy. Yeah, my selection can be fluctuating around, right? Depending on your luck, right? And different people run it differently, depending on yeah. So it's not trustworthy, right? And what's the reason of this? What's the source of this randomness? Sorry? Smaller data set? Why, when data is small, you have such randomness? Why every time we run it, we get different number? We're doing the same models.
Because your testing and training data are changing.
Yeah, because we have the random split, right? So that's the randomness. So that's unnecessary randomness we are introduced into this picture. We already have a lot of randomness. We said the data sample we have on hand, this 392 data points, is a random sample already. We are struggling with this randomness in the data sample. And now we're splitting that into 2 by adding another layer of randomness. And in order to deal with the first layer of randomness, we are introducing another layer of randomness. So are we really solving the problem or creating more problems? Okay? So that's a bigger question. And yeah, so that's a issue, right? But so how do we solve this? If you don't have a better way. So we have a better way, right? If you don't have a better way, how do we solve that? But so we just take an average, right? So that's if computation is not a concern. If I worry about this line is not very stable, it's going up and down, I just repeat that 100 times and take an average. Yeah? I can take an average. By averaging, I'm taking out this randomness, right? So the first way of dealing with randomness is averaging. Right? Repeat the same process many times and take an average. So you can take an average. Hopefully that's going to be smoother, and that will give you some quick answer. Right? But in many situations, that's not that easy by repeating the thing many times. Right? It's not an easy thing to do when you have a large data set. Okay? So let's see the pros and cons. So it sounds like a good thing because at least we have taken the first step of moving out from the in-sample errors, and we now can talk about out-of-sample errors. That's a bad thing, but that's fine. Right? Also, we're talking about computationally, theoretically, we just need to do that once. Right? We just run the model once, actually with half of the data. Right? So it's going to be faster than before. Right? So that's computationally that solves. It doesn't add new problems. Bad things we have seen. On the first level, we only used the half of the data. Right? Before we have 300 something data points. Now, at the time of building this model, we are only using 196. Right? We already have a limited amount of data, but now we are only using the half to build a model. Okay? So we're losing some some of the information in the other half of the data, right? We reserve that for the kind of a mock exam. But how do we deal with that? How do we deal with that? That's not a killer kind of a issue, right? That's an easy fix for that. And in practice, we should have later we'll talk about a more general fix. But keep in mind what we are doing here. I think that's important. So we start with the whole data. And we say let's split into the training part and the validation part. Right? We randomly split. And why are we doing this? We want to, so the ultimate objective for us is to, in the chat, there's a chat. That's over there. So the ultimate task for us is to do model selection. Because we have 10 models out there, we don't know which one to choose. Right? So at the end, what we want is a model selection. And what do we mean by model selection? So we said we have n models, and we have 10 models. The take home is, the nice thing is if we can say, yeah, n is 2. Right? That's what we are trying to do. Do you all buy this idea? That's what we are trying to do. And all the way up to this point, we have been using half of the data to reach that conclusion. We use the half of the data, train all these 10 models. We compare these 10 models on the other half. And at the end, we say 10 being 2 is the best. Right? But this whole process is the so-called model selection. But we shouldn't just stop there. If we stop there, we say, yeah, we have trained 10 models. Let's pick the one with n being 2. We know that's the best one. We use that model to predict future y. That's not the right thing to do because that model is built on half of the data. Right? So the right thing to do is let's take the output, the result, and go back to the data. Now we know n is 2. We have chosen the best model. Let's apply this best model to the full data set. Right? To make full utilization of data for the sake of predicting the future. So things in that square is the model selection process. And keep in mind, in this whole process, we are just selecting one model. We're not training anything. The only take home is n is 2. It's better than n is 1, better than n is 3. That's it. And after knowing n is 2, we need to go back to the full data set and do the whole thing again with n being 2. Okay? So we don't really lose any data in this case. We're still using everything in training the model. The process in the middle is the model selection. In order to select the best model, we have to split the data so that we can estimate the out-of-sample error, all these things. Right? But that's not where we should stop. Yes?
Bring the n equals 2 back to the data. What are you trying to do?
That's to retrain the model. So what do we mean by n is 2? So now we believe mileage per gallon should be a quadratic function of the horsepower. And we have trained that model earlier with half of the data. We have obtained beta 0, beta 1, beta 2. Right? But that's not the point. The point over there is not to get a model. The point there is to have a horizontal comparison. After having that comparison, we know n is 2. This is our model. We go to the whole data set. Let's train everything again from scratch. We should get another beta 0, beta 1, beta 2. And that's not going to be the same here because that's double the data. Right? But that's my final model. And my argument is that final model is going to be better than this model we built in the middle. Right?
Will you have a case where you first have 2, n equals 2, then when
No, you no longer compare. So you have done the model selection. You have decided n equal to 2 is my model. So I just go back and find the betas. Right? So this is when you are struggling whether I should use k-nearest neighbor or linear regression. The same thing. I run validation. I compare these two things. I say, oh, k-nearest neighbor is better than linear regression. So I should use k-nearest neighbor as my final model. Then I go back to the whole data set to run everything again with k-nearest neighbor. Right? So everything in the middle are not going to be kept. So there are a lot of things in the middle. Later you will see we will train like hundreds of models in the middle. This is just horse race. There are many horses are running out there. But at the end of the day, there's only one horse, but you don't even use that horse. Just keep that parameter, and we are going to train a better horse, right? Okay. Next week we'll talk about the big flow. Next time is the exam. Next time we'll talk about the big workflow. But just keep in mind, all that we have been doing is to find a way to facilitate the selection process. It's just a selection. Right? And other things are not taken home. So that actually solved the problem. We are not underutilizing the data. Right? And but if you really have to use that one, that's what you have. Earlier we said this is the error we obtain here is going to be an overestimation because the model you're talking about here just used half of the data. Right? Back to the picture. So we say if we choose 2, we got a 19 here. That's going to be an overestimation of the true out-of-sample performance when you train your model again with the other data set. But the issue is when you train your model again with the whole data set, you will never know what's the error there. You no longer have a data set to evaluate that. Right? So that's going to be the number you have, the only number you have available, 19. But we know that's an overestimation. The true thing we have should be better than that. Right? But yeah. And there's a variability we have talked about. Because of the extra randomness we have introduced, things becomes more random. So we get a different lines every time, right? So how do we solve that? There's a smart idea, the so-called cross-validation comes in here. Yes? Mm-hmm.
The previous example, if you had started with a full data set and you did all the validation error for the degrees of polynomial.
How do you have validation error? You need
using a whole data
to
set.
train your model?
Yeah.
Then you only have the in-sample error, not out-of-sample error. So the whole idea is to separate. Huh? Yeah. It's possible, but you cannot trust that.
One big round to get that. But you did a big cost race to get the done.
How do you know 2 is better?
You just plot the line.
That's the in-sample error. What kind of line you want to plot? Mean squared error?
How did you get 10 random?
No, I don't have. No, I'm repeating the process 10 times. I'm redo everything. The first time, let's split. I do everything. I get 10 errors. I said, let's go back, resplit the data in another random way. Do the same thing. You get another line. That's the 10 lines. Right?
So you average it out, choose the end.
Yeah, you can average out this thing if you worry about that. Yeah, but we have a better way. I just say if you stuck here, you have to go home now. You remember to average, but we have a better way. Right. What is sensitive to outlier?
Because the model will be overfitting. Because, for example, if somebody is very outlier, so it will be very sensitive to the maximum number.
Here we're also using that, right?
Yeah, but if we split into 2 samples, right? So maybe sometimes the maximum will be in the training sample, sometimes the maximum is in the test. I mean the
That's an interesting. So you're saying by introducing this randomness, we are benefiting from that.
Yes. minimize the effect of the outlier.
I can imagine. Yeah. Do you see the point? If there's an extreme outlier, if you're using the whole data set to train the model, that outlier is going to play a role there because that point is going to be there anyway. But when you randomly split, half of the time the point is there, half the point is not there. So when the point is there, you get 5 bad models, even worse than the original. But when the point is not there, you have 5 good ones. And by averaging, hopefully you can average out the effect, right? That's related to the random forest idea later. But, I see the logic. It may not hold. It may hold or may not hold. But yeah, it really depends on. But I see the point. Yeah. So by averaging, you might be benefiting from there.
Sorry, so just to add on. So before doing the modeling, should we take a look if, let's say, there's really an extreme data point, do we still include that to do the modeling, or do we take it out?
I don't know. The pre-processing is a tricky part, because without doing the modeling, you don't even know the impact.
Before you begin, probably take a look at the whole data set. There's some extreme data.
Yeah, but
in practice, do you just throw everything in and do the modeling, or you?
I would do the modeling first and see what's the impact. If there's some problem, I will go back and think about whether I should take out some of the data points. If without seeing anything, you just decide to take it out, it may not be safe, right? It may not play a role. Yeah. But that's another topic. Let's not worry about. Pre-processing is the art part. We're talking about the science part. All right. So let's try to find a way to deal with these 2 disadvantages. Let's try to come up with a way that makes higher utilization of the data when training the model. Let's come up a way that is not so variable, right? It turns out there's a smart thing designs to be done this way. So let me show you the picture. So the idea is let's still split the data into 2 non-overlapping sets. But now I'm going to only keep 1 data point in my validation. I'm using all the n-1 data points for training and just use 1 data point for the validation. But that's just 1 run. I'm going to repeat this whole process n times. And every time I'm changing the validation data point. In the first iteration, I use number 1 to be validation data. Next time, I'm using number 2. Next time, I'm using number 3. So I'm repeating this n times. So every data point show up exactly once in the validation throughout this whole process. Right? But the data points show up many times in the training set. Right? Whenever you are not in the validation set, you stay in the training set. Right? So I'm repeating this n times. And at the end, what do we have? Think about, I'm training this model n times. For each row, I have n-1 data points. I'm training my model. I'm predicting the y on the validation point. Right? So I have a y1 hat. In the first run, I'm coming up with a y1 hat. Second one, I'm coming up with y2 hat, y3 hat, yn hat. So every point, because they show up exactly once in the validation set, they are going to be predicted exactly once. So every point has exactly 1 y hat corresponding to that. Right? So at the end of the day, what can we do? We can just glue all these y hats. So this guy come here, come here, come here. What do we have? We have our whole data set and data points. And every data point has a prediction. And every prediction is being predicted without the knowledge of its true y. Right? Every point I, when it's being predicted, is predicted by a model without the knowledge about itself. So we're not cheating here, right? We're not seeing the answer and then doing the model. So we are not cheating, right? So we have a nice way of using only endpoints, but actually at the end we have a validation data set of endpoints, right? That's magic. That's magic. So what's the error? Earlier we talked about validation error. This is the so-called cross-validation error. And by the way, cross-validation just means the points sometimes in the training, sometimes in the validation, they're crossing, kind of cross-validate each other, right? And so we can just measure the errors. So every data point has a prediction that has an error. So we can just average all the error in this set. We have a nice whole set of errors. Okay? Right?
This is still the only one model.
For each model, we'll do the same thing. Yeah. This is just assuming I have one model. Okay? When we have multiple models, the issue is how do you loop over the models versus loop over the iterations. But we'll come back to that later. But now just give me one model. I can use that model to predict on each of the points, and I can measure the error. So that's cross-validation error. That is out of sample for sure, and that's a large validation data set, right? Larger than ever. In the previous one, we can no longer, we don't have endpoints. Right? Now we have a much larger one. Okay? So that's the idea.
When let's say we run the first time, we use the first data set to predict first model.
No, slow down. When we do that first run, it's the first row.
Yeah.
We use data point from number 2 to number n to build a model.
Yeah.
And we predict on number 1, right?
Yeah, correct. To predict number 1, what I'm saying is, let's say, do you know what are your terms, variable terms?
No, that's a given one model.
Oh.
So give me one model, I can do all these things and give you the error of that model. Okay. If I have 10 models, I can do this to the 10 models. Each model eventually will have an error. And then I can do the horse race, which one gives me a smaller error. Okay. For now, it's just given one model, fully specified. How do I estimate the out-of-sample performance? Okay.
Which model you choose out of 10 models?
We don't use the models. Again, there's again good questions. We are repeating this n times. Each time we are calibrating a linear regression model for horsepower. Remember the example? And there's a linear regression model for each iteration. But those are not going to be used. Those are just the horse racing with us, right? All that we are using is a number for each model. I'm ending up with an error measure. So I'm choosing which n is the best by comparing these 10 models. Right? At the end, your answer is still the same. N is 2 is the best. That's it. Then I throw all the models here. They are not going to be used in prediction. They're not. It's just a byproduct along the way. We will be throwing a lot of models. Okay. So let's see the good things and bad things, right? This thing is designed to deal with the issues earlier we mentioned. Number one, there's no randomness. We are looping over the whole data set. Each point show up exactly once. If you repeat the whole process, you will see the same thing exactly, right? There's no randomness at all. And we are trying to utilize the data. Every model is trained with n-1 data points. So when do the horse race, these horses are more trustworthy because we use n-1 points. That's the maximum possible number of points to do that. Right? But at the same time, there are bad things. Right? Bad things, computational, this burden is pretty big. Right? We are repeating this thing n times. Right? N is fine. In our problem, is 392. We will do that later. It's just several seconds. Right? But if you have 1 million data points, you're running 1 million models, right? So that's not going to be a practical thing in practice. But let me highlight only in some very special models running leave one out cross-validation does not hurt the computational requirement. There's several special cases. There's a least square thing, let's not mention that. It depends on the internal kind of a matrix, all these things. Think about the k-nearest neighbor. I think that's a beautiful idea when doing k-nearest neighbor. Let me make up a data set. Huh? Remember when we do k-nearest neighbor, I have a x1, x2. I have some y's. Right? Let's say k equal to 3. So that's a k-nearest neighbor model. Right? I have a data set with some 0, some 1s. The markers indicate their y value. And I have a k value. So that's a k-nearest neighbor model. Right? Give me an arbitrary point on this plane. I can find the 3 neighbors, and I can make a prediction for you. Right? So now let's worry about this point. So when we do k-nearest neighbor in sample, how did we predict the label for this point? We need 3 neighbors, right? Which one is the first neighbor? Now let's think about the in-sample version. This is the in-sample version. In-sample version is I have the model. I'm applying this model onto myself. Right? That's a cheating version. I'm applying this model onto myself. So the first neighbor is myself. Right? I'm using myself as that's the closest one, 0 distance. I need the 2 extra neighbors. Yeah, roughly. Right? I need 2 extra neighbors. So now I have 3 neighbors. I'm averaging them and coming up with a prediction. Okay? So that's the version without cross-validation. That's using in-sample way to predict. This is KNN in sample. So let me do a KNN with LOOCD. And let me try to replicate this data set. There's still a pattern. All right. So we're still talking about this guy, right? So we have a model. We still have the model k equal to 3. So now we're saying I want to evaluate this model. The data and k being 3 is a model, right? We said this. And for any point we can predict. Now let's evaluate this model by leave one out. What do we mean by leave one out? I'm evaluating this point, and then this point becomes my validation data. Right? That's the point I'm predicting, so that's the validation data. And I'm leaving that guy out. Right? All the other guys are still in my training data, so I'm leaving that guy out. So I need 3 neighbors to predict on this guy. Right? So the neighbors are still there, but I need 3. So I'm basically taking 3 other neighbors. So I'm basically changing the k nearest neighbor into k nearest other neighbors. Right? That's the same problem. I'm using 3 other neighbors to predict on myself, because myself is taken out as the validation, leave one out. Right? So you can do this for every data point. For every data point, you leave yourself out using 3 neighbors to predict. Right? So leave one out and the original k nearest neighbor, the algorithm is pretty much the same. You just exclude yourself, then you're done. There's no extra computational burden. Just because in the previous k nearest neighbor version, for each point you are looping over every point anyway. Now you are still looping over every point, so you are not hurt by this leave one out, right? So later I will show you in R there's a built-in function to do that. You just leave yourself out. And that becomes a super good model because you're no longer cheating. Whenever you're predicting on a point, you're leaving yourself out, and you can evaluate the error nicely. That's just a special case. It doesn't work for everybody. It just because k-nearest neighbor has such a nice structure, leaving one out exactly solve the original problem, right? And that's one of the computation issue is one of the concerns for leave one out. And there's another issue that is high variance. Right? Earlier we have a high variance somewhere, right? Earlier we talked about high variance. That's when we do this validation set approach. When we repeat that 10 times, we are seeing different lines. This is driven by the randomness from the splitting. Right? Because we're splitting the data randomly. Every time we run this, we are re-splitting the data. We are seeing this multiple lines. But in leave one out, we have no randomness. Every data point just show up there. Right? There's no randomness. How come there's still high variance? Right? So if you think about that, this is about the higher level randomness. Randomness in your data. The data is random, right? That's the first level of the randomness we're dealing with. So that's exactly the idea. Although we are running n different models along the way, these n different models are not very different. Not very different in the sense that every time you just take out 1 point and put in one point. So there are n points, and there's a lot of overlapping. Right? So that's exactly related to the earlier idea. If this is one outlier sitting there, this outlier is going to influence almost all the n models, and that's going to create some variance because there's tiny little randomness in your model, in your original data, will lead to some fluctuation of the final model selection. I don't have a good illustration of this thing. This thing you need to simulate a data set, simulate many data sets, and to see. Right? But let's stop there and let's think about a better solution. So we have introduced the two extreme versions. One is extremely certain and inefficient, the first one. The second one is extremely deterministic and also not very efficient. But it turns out there's something in between, and this is a so-called k-fold cross-validation. The idea is similar to the leave one out, but just say I don't want to every time just leave 1 point out. I want to leave a bunch of points out. So that's the idea. Right? The same thing, but there's another k parameter. This is not a k nearest neighbor. This is a k-fold cross-validation. So I'm basically cutting my data into k groups. In this example, that's 5 groups. Group 1, 2, 3, 4, 5. Right? Instead of cutting that into each point is one group, I'm doing that 5 groups. And every time I'm choosing one group to be used as the validation, all the other groups to be used as the training data. Right? Still the same idea, but the immediate benefit on this picture you can see, the immediate benefit is how many times are we running this? K times, right? Earlier we were running this n times. Now we are only running that k times. See, when k is 5, I just run it 5 times. Right? There's an immediate benefit from grouping the data. That's a thing, right? But all the other things are the same. We trained k models. For each time we use the model to predict on the validation stuff, and at the end we will try to glue them back. We take these guys here, take these guys here, take these guys here, take these guys here, take these guys. So at the end, what we have on hand is still the same thing. For the whole data set, for all the n points, we are generating some prediction that is out of sample, right? And we would have, for the whole data set, we have their true y, we have their prediction. Although the predictions may come from different models, but we have some predictions. And from there, we can evaluate whatever, mean squared error. This can also be like a classification problem. Then you have a P. Then you can do ROC, AUC, all the stuff we have done last time. Okay. Later I will show you how to do that. But conceptually, that's borrow the idea of leave one out, but trying to simplify that by dealing with the points in groups. That's the whole idea. Right? When we have the groups, we simplify the computations, but all the other things remain the same. And the overall cross-validation error is measured on the whole data set. So I just put the formula there, but it's not important. We basically put everything down. We have a whole data set. Everybody has a y and a yi, so I can measure the error easily. This is basically saying in some of the software package, in the middle of each iterations, it actually already calculated the error. So I have this bunch of points being used as validation. Error already, even at this stage, I'm calculating the mean squared error of this small group, group 1. Then I have 5 groups and 5 mean squared error by group. So I need to combine them into the overall error. So I need to do a weighted average kind of thing, right? Because the 5 groups may not be of the same size. Right? In practice, you cannot always make sure they're in the same groups, right? Well, you have 99 data points, right?
Iteration, how many rounds of training we need to?
One. We just have these data, just run the model, right?
Previously, we need to train this from order 1, order 2, all the way to order.
No, that's 10 different models. That's the 10 models we are choosing from. Now let's think about we only have one model, n being 3. I want to know how model with n being 3 performs. Right? So I'm going through all this whole process to get an error. I claim that's the out-of-sample cross-validation error of model 3. Then you can do the same thing for model 2. You get another error. Then you can compare them later. Right? But this is, again, for a given model. But I guess you're getting to the question like, shall we fix a model, then do the loop here? Or shall we do the loop here, then fix a model? So we can cut the data here, then compare all the 10 models in this here, right? That's a better way of doing things. I'm coming back to the details. How do you sequencing the loops? We are going to have 3 or 4 loops later. There are many. We need to sequence that, which to put it out. Okay. Any other questions? Good. So that's the conceptual things. So we can do that on the automobile data. So this is what we have seen, the 10 repetition of the validation approach. This is the leave one out. We said this is a deterministic, so it makes no sense to repeat that. So that's going to be the leave one out. And that's the 10-fold cross-validation. I forgot to mention, when we do 10-fold, k-fold cross-validation, we are bringing back the randomness back to the picture again, right? Because we are allocating the points to the 5 groups. That's not a good representation. We're not just say the first 20 goes to group 1. Yeah? We are randomly allocating them to groups, right? And that creates some extra randomness. But if you look at this is also 10 independent runs. So the variability here is much larger. Variability here is almost nothing, right? So still manageable.
In k-fold cross-validation,
Uh-huh.
so is the selection with replacement or without?
Oh, sorry, with
Is
replacement? Oh, no, it's just allocation. So you have endpoints. All the endpoints should go to these 5 groups. We talk about how do we do that. There are multiple ways, the good ways and bad ways. But yeah, every point has to be assigned to a group. Right? You need to use all the points.
How do you choose the optimum case?
That's an easy question. K is 5 to 10. Later I'll show you. Let's try different case. So I said I have four different loops. I have a loop over this 10 repetition. I have a loop over different K for the K fold. I have a loop over 10 different models. I have some other loops, I don't remember. So you can compare everything. Yeah. But K is in general an easy decision because almost universally K in the range between 5 to 10 is good enough. So not very much dependent on the data. Right? And these are some pictures we may have seen in the first session where we talk about in sample, out of sample. We say that the true population is a nonlinear black line, but if we don't see that line, we only see the data points with some noise, we may fit a straight line. That's an underfitting model. We may fit a high order polynomial that basically connects all the dots. That's an overfitting model. So we are not really sure how to find the best order of polynomial in this case. Right? Last time we said if we have a test data, we can easily measure the test error. The blue guy is the test error that was mentioned earlier. And if you have the test error, you can choose the model gives you the smallest test error. Right? That's easy. This is a simulation, so you can always have a test data. But if you don't have, what do? You can only do the cross-validation. So here we have the leave one out and tenfold cross-validation. That's these two lines, the black and the orange, these two lines. Right? So the message on this picture is the test error and the cross-validation error are not exactly the same. Just think about this is no magic. We only have like 50 data points. We managed to draw such a line with the same 50 data points. Right? That's already a big magic. There's still some gap because all these things are, just as we emphasized many times, all these things we have done, they are derivatives of the data sample we have. The data sample is small and random, so everything is still going to be random. But the point here is they are not going to approximate the test error very closely. But if we just use this guy to do model selection, we are pretty safe. The model selection says, hey, here we should choose 8. Here it says we should choose 6. Not very different. You can try that on many different other situations. Again, this is simulation, so you can design your own difficult kind of context and try to see how the discrepancies will be. So this is also the best model according to test error and best model according to cross-validation error. Best model according to test error versus validation error. Right? So it just said the absolute number may not be trustworthy, especially when your data set is small. Right? But using that to do a model selection is much better. It's better than in sample. Right? Much better than the other things. So you can see at the end of the day, we have introduced the 3 different validation methods. Validation set on one extreme, leave one out on the other extreme. And k-fold is somewhere sliding in between because you can change the value of k. Right? When k is equal to n exactly, we are getting to the leave one out. Right? We have n points, we split that n points to n groups. So every point is in one group. When k is equal to 2, it's not exactly the same, but we have split the data into 2, but we still do cross-validate, right? Relative to the validation set, that's not exactly the same, but you can imagine by changing k, we are sliding from one extreme to the other extreme. So how to choose k is the next question. I have answered that question already. The rule of thumb is between 5 to 10. If you can afford, do 10 when the data is not big, right? K being 10 means you are running this 10 times, right? If you can afford computationally, that's fine. If the data is too big, go back to 5. That's doable. And that's empirical observations. There's nothing so special. And we didn't talk about, we also spent some time on classification, actually. There's nothing more complicated than that. We said, as long as you are running cross-validation, at the end of the day, you have your data from 1 to n. For each data point I, you will have a yi. That's a true value in your data set. And you will have pi hat. That's your estimate coming up by the model along the way. Right? So last time we talked about how do we evaluate all these different situations. Right? For a classification problem, if you have the true y being plus 0, 1, and if you have the probability, you can do all these things. Misclassification error. You can do true positive, false positive, true negative, false negative. You can do ROC. You can do AUC. So with that, you can do anything. Right? There's nothing new relative to the last week's stuff. The new thing is this guy. Last week, we come up with the probability with in-sample models, logistic regression. Right? This time, along the way of doing cross-validation, the probability are just generated or predicted out of sample. Right? So there's different probability, but the rest of the flow is still the same. So later I'll show you how to plot all the AUC, the ROC kind of thing. Right? Okay, good. So later we'll spend some time on our old friends, the mixture data set. Where just a quick review of your homework. If we're running logistic regression using order 1 polynomial, you will get a straight line to split the data. That won't fit the data very well. So you need to increase the number of orders. The more you increase, the more curvatures you will see. And at the end of the day, we need to choose the order of polynomials to some extent. Right? Later, I will show you the picture of the mixture model. Last time, we have done the test error. That's a simulation. We have the test. And we have done the training error, which one is the one going to 0. Today, we can add the validation error. Which one is validation? The black one. That's a validation error. So it's again, the same message. Validation error can be used to do model selection. It's doing a good job telling you what you could have seen if you have a test data set. Yeah? And a quick thing is, when you are doing your horse race, it doesn't have to be the 10 models from the same family. So you can also put your k-nearest neighbor into the same horse race. So I have 10 models from logistic regression. I have 20 models from k-nearest neighbor with different k. Then just race, right? Just for each model, I can evaluate the error. So there's nothing stopping us doing that. Yes? Yeah, this is simulation. Simulation, yeah. Simulation, you're playing the role of God, so you get whatever you want. Yeah, but you shouldn't use that information in changing your model. You can only use that information in measuring the error. If you use the test data to change your model, do model selection, that's no longer test data. That becomes validation data. So you are manually expanding your data set by having some more information so that you can do your model selection. So just if you are doing simulation, make sure which row are you in. In the God row, you see everything. But you shouldn't use that information to help the other guy. Right? You can only evaluate how this guy is doing. Right? All right. So it's pretty much done. The conceptual part is done. So we spent most of the time on coding. So I have the 3 files first on different versions of cross-validation. What are the important things? So we will do cross-validation on generalized linear models and k-nearest neighbor. The thing I want to highlight is in R, for majority of the tools, there's a built-in cross-validation function. Like we have done GLM last time. We can do cv.glm. It does that automatically for you. It's really a black box thing. You say, this is my model I built last week. Now do a cross-validation for me. You just say, okay, the error is 24. Later you will see, this is the model I have last time, do a cross-validation. That's it. And for k-nearest neighbor, there's also a built-in function, kn and cv. Some are very good, some are not very good. Later you'll see why. But in some serious situation, you have to do the cross-validation manually. Manually in the sense that we have to cut the data into groups manually. And for each group, we need to do the k iterations to evaluate the models manually. And there are many situations you have to do that manually. So I'll show you the black box version. You may like it, but yeah, let's do the black box version first. But I really hate those things. So let's do the GLM validation first. GLM validation. This is pretty much replicating the pictures in the slides. I just show you how to plot those pictures in the slide. So this is the auto data. Well, there's nothing important about the auto data. It's a nice cleaned with 9 columns. So nothing to worry about. Number of rows, 392, right? We need to keep track of the number of rows because we are going to split this data. Okay. So let's do the validation set approach. This thing has no built-in method. Earlier I have shown you the built-in are all for cross-validation. Yeah, virtually nobody is doing the standard validation set. Just for the sake of the illustration, let's do that, right? So now I'm starting the loops. I'm having 10 repetitions. So that's what I call run, right? I have multiple runs. Then I have multiple models to choose from. That's a polynomial. That's horsepower to the power of 1 to 10. That's indexed by I. So that's 2 numbers. The first thing I'm doing is I'm creating a data frame for saving my result. Later I want to make a nice plot. So I need to make sure the data is in the right shape. So let me run it, you will see. So what I'm doing is I'm creating a data frame with empty answers there. I'm going to enumerate my model from number 1 to number 10. I'm going to repeat this 10 times. So in total, I should have 100 observations, 10 by 10. For each of these observations, I should have a mean squared error. For each model, in each run, there should be a mean squared error. So I'm just constructing this guy, so later I can fill in the numbers in this whole data frame. Then I can have the nice plot. This expand grid is a handy function for doing the full combinations. I have 10 models and 10 runs, so it does the full combination, give me 100 rows. Okay? Stop me if I have anything, right? Or it's too fast or too slow. Or run is my index. This is the total number of repetitions I would do. I'm going to repeat things 10 times. So you can ignore run first. Let's ignore run. Let's just do once. Right? Later, let's ignore this whole loop. Let's do once. The first step, what do we need to do? We need to split the data. And the easy thing in R is we have 300-something data points. So moving the data points around is not smart. They're typically big, right? So when we split the data, we really kind of say point number 1 goes to the training set, point number 2 goes to the validation set, all these things, right? We basically deal with the index. So what I'm doing here is I'm generating a train index. That's a collection of the points, the index of the points going to be in the train data set. So that should be, I'm sampling out of this 392 points. So that's the 392. That's the total number of points. I'm sampling 50% of that. So that's 0.5 times that, times the total. I'm rounding that to integers in case this is an odd number. Let me show you what's the output. So the output is 196 index. It says I have, in the training data set, I should have 0.12, 0.80, 0.182. Right? I'm selecting 196 points in my training sample. Right? Later, I will just pull the data points. And the beauty in R is once you have the training, validation set can be just negative of the training index. So the positive ones means I want to include this data point. Minus 12 means delete this point from my data. Right? So one half I'm keeping the 196 data points. The other one I'm deleting the same 192 data points. Okay? So ignore the run part. So we are going to do this once. We have split the data into two parts. We need to compare these 10 models on this splitting. Right? That's related to the early question. Shall we do the model loop first, or then do the loop, do the split? So here it's obvious we should split the data first, compare the 10 models on the same splitting. So we have 10 models. Let's do model number 1 first. What is model number 1? It's a GLM model, mileage per gallon versus horsepower to the power of 1. Data is the whole data set auto, and the special thing is this guy, subset. So that's some arguments in the GLM package, and pretty much in all the tools we're going to do, there's a subset kind of option. So you can specify which subset of the data you want. You say subset is my train index. I'm only keeping those data points. Okay? So that's just a GLM model built on the 196 data points. If you want, you can see the summary. That's just a logistic regression model. Okay? We are done with the model. We can predict. Now we are using the fitted model to predict on the new data, which is the validation data. Right? So I'm subsetting the auto data by selecting only those inside the validation data set. So let's see what the output. Oops. The output is 192 data points, 96, and they're y hat. Okay? And having that y hat, I can measure mean squared error. What is a mean squared error? The true y. This is the true y, the true MPG from the data, minus the prediction squared, then mean. Yes? Mean squared error. What is the number? It's just one number. Right? So this is one number for model 1. Right? If I do the loop, forgot to run. Is there any question for this one run? At the end, for each model, I just have a mean squared error. That's all I want to know. I don't save the models along the way. I'm not going to reuse that. So the resulted thing is for each model, for each run, I'm repeating this. This is already 100 times done. I'm saving the result, and I'm plotting it out. Right? That's the 10 lines you see on the slide. Any question? No? Okay. Okay. So in your homework, did you use this polynomial function? You know the raw thing? Okay. Just use that. There's some ugly transformation. If you don't do the raw, it changes your data by normalizing it. So it's changing all the beta parameters. It's after the normal. So the poly function generates the polynomials, right? If you say poly 3, it takes the x and generates 3 columns, x to the power of 1, x to the power of 2, x to the power of 3. Should be 3 columns. Then you run your regression, you get the 3x, you get a 3 beta to that. But without specifying the raw thing, it re-standardizes your data in some sense. And so it rescale your data to some extent. And therefore, the resulted beta are different. It doesn't matter if you're using the GLM function to predict on the future, because it knows it does the transformation. When you have the new data, it does the same transformation. So you don't lose anything. But when you are carrying that beta outside in some other context, I believe that's my beta, that's my linear model. I'm plugging the data in some other context, you're in trouble because you don't do the transformation. So I had a big lesson from there. Somehow by default they change the data, so you have to specify. Don't mess up my data. Just leave the raw numbers there. Okay, so that's the validation set. So we would say goodbye to that guy. No more validation. So let's do a cross-validation. As I just said, there's a CVGLM guy. That's in the boot package. So you need to install a new package. There's a function called cv.glm. This is a weird function. So it says, if you already have a GLM model built in the past, tell me that model and give me the data. I'm going to run cross-validation for you. So you have to have a model first. So just imagine last time you do the homework, you have the GLM model already. You can just throw that GLM model to this CVGLM kind of function together with the data. It just does the cross-validation for you. Let me run that. It's not very intuitive, but you need to do it in 2 steps. Build a standard GLM model and put it in. So it's done. If you see what's in there, there's nothing in there. You just see what's the command that you use to call this function, what's the number of folds. We didn't say anything about the fold, so by default it's leave 1 out. So the number of fold is the number of data points, 392. And the bunch of seeds are not important. The only number we want is this guy. That's the cross-validation error, 24.2. That's it. There's another error. It doesn't matter. In some situation, there is a bias, and they need to fix the bias. So there's an adjusted version of the error. But let's just use the first one. So in our context, it's safe. So all that this thing is given, what's the output? The things we obtain from this function is this 24.2. That's it. Later. Cost is by default. It needs to measure the error of your model out of sample on the cross-validation. What error you want to measure is specified by the cost. Here we are doing regression. The default error is mean squared error. So if you're just using mean squared error, you don't need to do anything. But later we will do classification. And cost can be many things. Misclassification error, AUC can be a cost. You can define whatever cost you want. It does the calculation for you. But for now, let's not worry about that. So think about what it does. This guy internally, if you're a geek, you can try to read the source code. Not very long. All right, that's it. So this is a good exercise to try to read all these simple functions. This is how we learn all these different way of cutting data. This is the line they're trying to cut allocating data somehow. And this is a loop over all the folds to do the model. And this is the calculating the error, all these things. It looks complicated, but not much substance in there. But internally, what it does, it first gets the formula from your the GLM object. It needs to know which guy is X, which guy is Y. That's the first thing. Then it's leave one out, so it has a big loop of 392 runs. For each loop, you take out 1 point, using that formula to build a GLM and do the prediction. Okay? And aggregate the error at the end. So there's an error, CV error aggregation thing. Where is that? This is the cost part. Okay? But anyway, if all you want is the cross-validation error, this is just one extra line of code. That's your cross-validation error. But that's for model 1. Right? So that's a quick example. Now we need to do model 1 all the way to model 10. So I'm again creating a data frame for saving the result. And I'm looping over model 1 to model 10. There's no repetition here because this is a deterministic. So inside, this is just the 2 lines we have just run. Build the GLM object with the particular formula. Then call your CDGLM and keep track of the delta 1. That's the number we need. So it is done. And if you plot it out, that's the second picture we have seen. For each model, there's a number. Right? We just get 10 numbers and connect them. Right? That's it. We good? How do you like this CVGLM? We can do much better version. So that was leave one out because we didn't specify the K. Now we can do the K-fold. If we want to do K-fold, the only thing extra is to specify K here. Right? Nothing extra. And because when we do K-fold, it becomes random again, so we have multiple runs. So I have a outer loop in the multiple runs. It takes some time. And that's the picture. That's the third picture in the slide. That's the 10 runs of 10-fold cross-validation. Are we good?
How do you decide the number of runs?
No, it's just for illustration, not very important. In practice, I would do 2 or 3 times, plot them out, and see how much is the variability. If they're close enough, I don't worry about that. If they're up and down, then I'm doing several more runs and to average them. Right? This is good enough. I don't think this 1 or 2 or 3 is good enough. All right, that's another one. This takes some time. Let me run this and we can have a break. So the next issue is we need to decide K. We talk about the K-fold. We said empirically we observe from 5 to 10 is a good number. But let's just do a crazy experiment. So I'm trying K. The minimum K is 2. Right? You can only do 1 fold. Minimum is 2. I'm trying to do from 2 to 30 folds. And because this is highly random, I need to repeat this 50 times just to take an average C. Right? So there's nothing new, but the special thing is I cannot afford doing all the 10 models. I'm doing model number 7. Number 7 turns out to be the best model. Right? I'm just doing the number 7. And for the same model, I have one model. I'm repeating that 50 times. And each time I'm trying from 2-fold to 30-fold. Right? Okay, let's have a break. So it takes some time. It's 1,000 something, right?
Number, because the K4 is just a way to validate, right? Now it looks like we are trying to find the validation number which gives you the best result. But probably if the case, maybe k equals to 10 is actually the real one, which is more accurate. But now you are trying to find the k equal to 7 because it gives you better result. Does that make sense?
Yeah, so the right way is you should start with a simulation. So you know the true answer. You know the true test error. Then you try depending on how the implementation. I think they have a pretty bad implementation. Later we'll talk about when we do that manually, how to release that. The last one is week 13, the last week. All right. So it's finished. What we have here. What we have here is we tried all the k from 2 to 30. Right? For each k, we'll repeat the whole process 50 times. So for each k, there are 50 points up and down. So that's the mean squared error of my model 7. Right? But when k is small, this is highly variable. When k is large, it's more stable. Right? And I have the mean plotted here. So the red line in the middle is the average mean squared error. And there's a range. The range indicates the standard deviation or something like that. It tells you the variability. Okay? So you can see up to 5 to 10, that's pretty good. Going further up doesn't add too much. So that's why people typically do tenfold. Right? That's roughly a universally true situation. It's really independent of the data, how big, how small. Roughly always do that. So that's an easy decision. So if you can afford, do that 10 times. Right? And there are some extreme situations if you have a really tiny data set. So you have 27 data points. You say, yeah, I learned I should do tenfold cross-validation. That may not be a good idea. 27, I would rather leave one out. Just run it 27 times. That's much easier than splitting the data here and there. Right? So that's a final message for choosing k. And yeah, if you don't want to look at the numbers, you can also calculate for each k what's the corresponding mean and what's the corresponding standard deviation. Right? So this is the most beautiful package you should learn. dplyr automatically reorganize the data into the shape you like. So this is GLM illustrated on CVGLM. Next, let's do our old friend, the mixture data, using k-nearest neighbor. So this is KNNCV. Right? So you should by now be very familiar with these lines. Right? We have seen this at least 4 times. Right? So I don't need to explain this, guys. Test data, we have seen that many times. So I just leave the test data there. So what I'm going to do, let me show you how to do k and then with leave one out cross-validation. So this is earlier the CVGLM can do leave one out or can do k-fold. This guy only leave one out because of the special structure we talk about in k-nearest neighbor. There's a special structure. So it doesn't have a k decision. This k is for k-nearest neighbor, not for the k-fold. Right? So you don't have a choice how many fold. It's just leave one out. So we can do a test. So you can see that's kind of easier than before even, than the KNN itself. You just need to tell me the x, the y, and how many k. I'm pretty much done. Right? Earlier we have x, y. That gives us a model, and you need to supply a data set to predict. Here there's nothing, so we are predicting on ourselves. This is a cross-validation. So let me run that with 15 neighbors. Let me show you what's in there. So after running this KNCV, the output are like this. So this is exactly what I meant in all the way up. Here. So what we have is this guy. So we have a data set with n points, and every data point has been predicted once. Right? So that's the output here. So we have in this mixture example, we have 200 points, and everybody is given a label 0 or 1 somewhere. Right? That's the label prediction. And if you are curious we didn't put the probability here because we don't really need a probability. If you want to plot ROC or those things, you can add a prob equal to true. Then you will have a probability guy there. Right? So that's not relevant here. There are also other information about the 15 neighbors that have been used. So for each point, I'm searching for the 15 neighbors to generate the prediction. So this is 200 by 15. So 200 points. So for each point, I know who are the 15 neighbors that have been used. Those are the index of the points. Right? So this is point 1 has been using these guys as the neighbors. Right? And also the distance measures from the point to all the other neighbors. It's not so critical. What we are going to use is only here. We are going to use these labels because we want to compare how many errors it makes using cross-validation. Right? This is the out-of-sample predictions. So that's a quick illustration of how to run that. What I'm going to do is I'm going to do a horse race. I have many possible number of neighbors as a choice. So I have this bunch of models as model candidates. I want to choose the best one. Okay? So we have already done this, I think, in the second session by using the test error. What we are doing here is just add an extra column that is the CV error. Right? So we have plotted training error and test error in the past already. So the only thing new is the CV error. There's some CV misclassification. So I'm creating an empty placeholder to hold this number. So I'm looping over all the models, so all the models with a particular K. These are the lines we have done earlier to train the model on to have the training model, have the model on the test data. And this is the new line we introduced today. That is the KN and CV using the X and Y. Right? There's nothing new other than that. And last time we measured the training error and the test error. This time we are adding this extra line of cross-validation error. So the cross-validation error is comparing the predicted class versus the true class. As long as they don't equal, we count as 1. Right? We count how many mistakes we are making divided by the total. Is that clear? And the algorithm is what we have been discussing in the slide somewhere. This is the algorithm, right? For each point, get the number of neighbors and average over the neighbors. Uh-oh. Something bad is going to happen. Oh, not crash. Okay, that's out. So at the end, we have the output. We are comparing all these different cases. We have measured the train error and test error last time. At this time, we add an extra column that's a CV error. Okay? So we plot those guys. That's the plot. So we have done the red line and the blue line last time. And the green line is the new one we have introduced. We said red line, this training error in sample going to 0 at the end. 1K is 1. Blue one is a test error with a huge test data set. So that should be the out-of-sample error approximately. The green one is the cross-validation error. Right? It's not that perfect in the sense that it went below the irreducible error. It shouldn't happen that way. But in terms of a model selection, this is almost as good as the test error. It tells us which model is the best model. This is number 3. What is the number 3? K being 5. Right? That's the third point is K being 5. And if you use the test error, you would choose number 4, K being 7. Right? That's pretty good. And if you see the test error out of sample 5 and 7 are not that different. so you don't lose a lot of things out there. Okay. Are we good? So the CV error at the end of the day is for model selection, right? And the k-nearest neighbor is a very special case. After selecting the model, you don't really need to rerun everything to do your prediction. The model is there. The model is the data set, right? Once you have a k, you are done. That's what you can predict. Next, let's do this thing using logistic regression. So that's going to be almost the same as your homework, your last homework, using the logistic regression on the mixture data samples. But the homework is in sample. You use is there any model selection? There's no model selection, right? I just tell you to do first order and sixth order polynomial. There's no model selection, right? Here we're going to do something. So that's the same data set. I don't need to run all these things. And cross-validation. Earlier I mentioned I'm going to have multiple layers of loops. And they're all kind of 10, so I changed the numbers. Otherwise, it's too confusing. Earlier I have 10 models, I have 10 repetitions, I have 10-fold. So I just changed all these numbers. So we are still doing 10-folds, but I'm having 20 repetitions and just 9 models for the polynomials. So let's first see how to do that using the CVGLM. Earlier for the automobile data sets, when we do CVGLM, that was for the regression context. So that's relatively easy. You just need to say, what is your K? For this guy is a classification problem, so there's a little bit more work to be done. But this is the same. I'm constructing the data frame for my final result. For each model, each run, I should have a place to keep the error. This is no longer mean squared error. This is going to be the misclassification rate. So that's a cost guy. Let me leave that for a while. So if you ignore the cost, we're basically doing the same thing. We have a loop for the repetition. We have the loop for the models. Then within that, we construct a standard GLM model with ith order of polynomial for x1 and ith order polynomial for x2. That's your homework when I is 6 or 7. This is logistic regression for the binomial family. And we are using all the data. So this is just constructing the model, right? We are not actually using the data. Then we can call CVGLM as before, specifying the data set and the model we just built and the number of folds we are doing, k-folds, right? The only thing extra here is the cost. That's the special thing in classification. But if you ignore that, we are just pulling this delta number and saving that to our result data frame. Are we okay? So the cost thing is a bit flexible in this function. The cost itself is a function. You can design whatever way to calculate the cost. So we need to specify this guy. So I'm really defining a function. And as I said, in classification, how do you measure the error? Where's my classification? Here. In classification, how do you measure the error? There are multiple ways to measure all kinds of error, but the inputs are basically the true class of each point and the probability you have predicted. Right? So give me these bunch of numbers, I can calculate anything. Right? And that's exactly the cost function. So I know you can calculate anything, but tell me which one you want. So that's a function. Input is the true y, and it's the probability. And I'm calculating the misclassification rate. So what I'm doing is I'm using a naive cutoff, 0.5. So whenever p is larger than 0.5, I'm predicting y hat to be true. Whenever p is not larger than 0.5, I'm predicting y hat to be false. then I'm comparing the true y with my predicted y. Right? I'm counting how many errors when the two don't agree with each other. I'm taking an average. That's the average error. So that gives me the misclassification error. Right? So if you want to be more creative, you can design all kinds of error measure. You can easily put an AUC into that formula. Right? I'll give you this thing. You can always calculate AUC. Right? But here, let's do the simple version. And we run that. So this is exactly the feeling at the exam. Just staring at the screen. It doesn't stop. So that's the misclassification rate for the 9 models. We have 9 models for I going from 1 to 9. The 9 models, we are repeating that 20 times, so there are 20 lines. There are 20 lines, right? That's the same thing as before, but just the error measure is different. Now it's not an MSE, but it's a misclassification error that we have defined in our cost function. Are we good? This thing? I claim this is a bad way of doing this. Do you spot any issue here? The issue is exactly coming from the black box CVGLM guy. So let's think about the sequence of doing these loops. Which loop should be at the outside? Which loop should be the inside? Right? So what we are doing now is repetition run is the outermost loop. That's fine. I'm repeating things multiple times. Right? The next level, I'm doing my model. I have multiple models, so I'm looping over all the models. Then within each model, what do? Within each model, we do CVGLM. We do CVGLM. Right? CVGLM inside itself is a loop. What's a loop? There's a k-fold. There's a k here. So this is the loop over the k-fold. Okay? Do you think that's a good way of doing this? If not, what's the issue? Select the you want to move the model outside?
Because data is changing inherently.
Data, yeah, that's the good thing. That's the issue. Where do we split the data along the whole process? Where do we split the data? Inside here, right? Before we run the k-fold loop, so we do the split here. We split the data into 10 folds. Then we loop over the 10 folds, right? So that's right before the inside CVGLM. So that creates a problem because earlier we said we want to split the data first. On the same splitting, we want to compare these multiple models. So that's a fairer comparison. This is not fair because when you do model 1 and model 2, you are talking about different splits. On average, they are fine, but it may not be the most efficient way of doing things. So I really want to swap this thing. And you cannot do that because you're stuck with the CVGLM guy. This is automatic. You cannot put your model in this guy. Right? So ideally, what do we do? Ideally, I have the run outside. For each run, I split my data here. I first split my data. And after I split my data, I have the loop over k. Right? I have a loop over k-fold. right? For each fold, I put the chunk 1 on the side as a validation, the other 9 chunks as a training. I have a training data. Once I have the training data, I'm looping over my model. On the same training data, I'm looping over my models. And each model will do some prediction. Every model will do some prediction. Then I'm redoing everything, right? So ideally, that's a fairer comparison because split should come outside the model. Okay? That's one of the motivation for us to give up on the black box method, because you don't really have any flexibility to change the sequence. So we need to do that manually. There's another motivation. Later we should see that. So keep in mind that's the bad way. That's the plot we obtained by doing this bad way. Right? Next we will do the good way. We'll try to plot the same thing again. Let's see how much benefit we derive from there. So that's the manual cross-validation. Then when we have to do that manually, then we are facing a lot of technical details. We need to split the data. How do we split the data? It's not that trivial. All right, so first I need to know how many data points are there before splitting. I need to know how many data points. I need to know what should be my k. I'm doing 10-fold, I think. My k is 10. K is 10. So there's a straightforward way of doing this is for each data point, I have n data points, right? For each data point, I'm equally likely choosing a group number for this data point. You go to group 2, number 1. Number 2, equally likely, you go to group 6. Number 3, you go to group 5. That's the straightforward way, right? So this is what I do here. So for each data point, I'm randomly choosing a group number between 1 to k. There are 10 groups, right? 1 to k. I'm choosing that n times with replacement. So the output is this. There are just 200 data points, so it's easier to read. It says point 1 goes to group 5, point 2 goes to group 6, 7, all these things. Right? But the issue is here. When you check the frequency of each group, you see any problem? They're not very balanced. Group 2 only has 11. Group 7 is fat. And I can do that again if I'm not happy, but there's always an 11. How come? There's a 13, right? So that's not a nice way of doing this. It doesn't hurt too much, but you are having 10 very unbalanced groups. Some are 13, some are 30. So that's not a good thing to do. So a better way, so we found out all these different methods from all these built-in black box functions. Just read the source code and see how they do that. Some of the black box methods use the first method, some using the second. And the second is much better. Okay? So what's the second method? So our motivation is when we have two groups, we should make sure those two groups are balanced. If there are 200 points, I should have 20, 20, 20, 20. Right? But also at the same time, I should make sure it's random. How do I specify 20, 20, 20, and at the same time make sure it's random? So there's a smart idea. It says, okay, I have these 200 data points from 1 to 200. Let me just give them fixed assignment, 1 to 10, the first 10 points, 1 to 10, 1 to 10, 1 to 10, 1 to 10. I'm repeating this 20 times. So every point has an assignment. There are exactly 21s, 22s, 23s, right? 20 10s. But that's not a random thing. Let me just shuffle that, and we get a shuffled 20, 20, 20, right? So that's the code we dig out from some of the functions. So it says, let's try to generate this 1 to 10 numbers. Let's repeat this many times so that we can fill the whole data points. So we have 200 data points, so let's just do 1 to 10, 1 to 10 all the way until we filled all these 200 points. Okay? And then we do a sample to shuffle that. Sample by default will just shuffle all these numbers, and that's what you get. Right? That's perfectly balanced. Right? All right. So we would use the second method. It's just a line of code. You can just always reuse that. So we'll do the same thing in this way. Right? Keep in mind we'll do things in this way. Think about the big loop. So I'm having, again, the data frame to save the result. Then let's see the big loop. So that's a whole loop. So I started by looping over the runs. Right? After looping over the runs, I do the split. I generate a fold. Right? Fold is essentially an assignment. It tells you where each point is assigned, which group each point is assigned to. Right? It's an assignment thing. So I'm generating that fold guy. So from here, you know point 1 is in group 10, point 2 is in group 4, all these things. Then I can loop over. I'm actually doing the model first, then the k-fold. Right? Here it doesn't matter too much. I'm doing the model, then k-fold. There's no fundamental difference. You can swap these two because I'm not doing anything in the middle. Right? What are we doing inside? Think about what was missing earlier. In CVGLM, inside the black box, there's a random splitting part. Then there's a loop over the fold part. So this wasn't there earlier in the CVGLM. For each of the folds, how do we do the things? Right? So how do we do the things? This is a k-fold cross-validation. We start with the GLM model. The same y and x, that's the same thing. Same logistic regression. Now the training data, what should be the training data? Everything other than the case fold. Yeah? We are setting aside one group on the side to be the validation. Then all the other things, as long as the data point is not belongs to the case group, they are in as the training. All right? Then the validation, we predict, using the trained model, we predict on the case group. So that's the validation group. We just do the prediction. This is the classification, so we need a response. That's what we talked about last time. We need a probability. So we save this probability. Maybe let me run that. Let's say we do model 2, k being 3. Doesn't matter. We can always run that and see what's in there. This is group 3. When k is 3, we are using group 3 where there are 20 data points. We're using group 3 as the validation set. And we make a prediction on these 20 data points. And we save the probability here. And the first row is the point index. Second row is the probability. So we are not so interested in the probability here. We just need a label. So whenever the probability is larger than 0.5, we put a 1 there, otherwise 0. So we convert the probability to the labels in the simple way. And we are counting the errors. So there's compare the y hat with the true y in the validation set. So that's the true y in the validation set. So we are comparing the error. The error, how many errors? 4 errors. So let me see the true y. What are the true y? Okay, 2 y's are pretty nice. So these 1s and the 0s are the predictions. These 1s and 0s are the true y's. So there are 4 errors, first 2, and there are 2 errors. Right? And I'm adding up the errors. So this is only the error I make in group 3 when we do tenfold. Right? This is only the error I make. So I'm saving that to the total error. And that's it. Okay, I can go back and run this again. Any questions? So the extra part is the splitting, is the fitting the model, generating the probability, and calculating the cost, basically calculating the cost. All right, so we can plot. What's that? This is better, right? If you compare it to the last round, this is last round. This is this. It's very subjective. But you can see at least they're more consistent, right? Less crossover. Keep in mind what are the issues we are trying to solve. We are not trying to deal with the variability over different runs. For different runs, it's still variability. What we are trying to deal with is over the same run, are your models compared fairly? Here is we have the same split term comparing the model. So over the same run, the same line, it's consistent. Here, I'm comparing the model on different splits. So you get all the up and down. Right? So you think look at the other lines, they're more consistent. Here you get all the up and down, right? For each line. Right? All right, but I guess in either way we reach a quick conclusion. Probably model number 7 is the best. Right? Next, earlier we have done this manual kind of a k-fold cross-validation. One problem we are trying to solve is this guy. We split the data and compare the model. And the other benefit we didn't utilize, that is, we have a lot of flexibility over this part. We have been using the misclassification error. So actually we can do the ROC and all these AUC crazy thing in the middle. So let me do that. I'm going to do the ROC in the middle. Okay? For each run, there will be an ROC curve. And that ROC is different from the previous ROC last week. Last week, the ROC was in sample, using the in sample data to predict all these things. Today, we're going to predict the ROC out of sample. Okay? And due to the computational issue, I'm just using one model. I'm doing model 7. Right? I'm doing model 7. I'm going to plot the ROC and calculate the AUC. So I'm saving the AUC later. So let's see what are the differences. Let me run it first. So I'm still having repetitions. I'm still having the fold, random splitting the data. I'm still having the k-fold here. Then within each fold, I'm still doing the GLM model and the prediction. So the only thing different is after this k, all that I'm taking away from this case fold is a probability. I'm predicting for the group 3, like earlier, I'm predicting a probability for each of the 20 points. Every point has a probability already. So I'm saving that back to my original data, and that's related to these guys. So I'm doing a group. For each group, for each point in the group, I'm saving this predicted probability here. And I'm looping over all the groups so that eventually I have a probability for everybody. Okay? So that's the difference. For each of the case folds, I'm just predicting the probability by using predict and typed to be the response and save that back. And at the end of this loop over all the k folds, all I'm going to have is a nice set of predicted probabilities. Then I can do the AUC ROC, and that has nothing different compared to what we have done last time. We need to construct a prediction object with the predicted probability with the true y. I can plot the ROC curve. That's the same thing as last time, and I'm calculating the AUC. So these 4 lines are exactly the same compared to last time. There's nothing different. The different thing is the input, is the probability. The probability is obtained out of sample. Okay? And you can see that's a picture. I'm repeating this whole thing 20 times. Each run, I have an ROC curve. And keep in mind, this is random, so repeating this 20 times, I have a 20 slightly different ROC. And AUC should be somewhere saved already. I have 20 runs. I have 20 AUC numbers. So you can plot it out. That's the 20 AUC numbers. You can take an average. So that's 0.85. So that's the out-of-sample area in the ROC, right? That's the end of the curve. Right? Every time you repeat, that will be different. It's driven by the split part, but we can average and get a pretty solid answer about how this model performs out of the sample. All good? Yeah.
Can we use the CVCFM for every time we need to do it manually?
Up to you. This is a taste issue. Check the exam paper last year. I'm asking for some plot you cannot get from here. Right? I'm asking for some plots. Next week you will see the answer. Right? Well, I'm asking you to plot the misclassification error and the false positive rate and false negative rate as a function of the cutoff. So by doing that, you don't get your things. Right? But at the same time, earlier over the break, there were questions like, why are we doing all this? There are existing softwares doing everything already, right? It's a personal taste. If you are comfortable with this thing, having no idea what's going on inside, that's fine. Right? And on the other hand, after you have done this once, when you see this black box thing, you can quickly check the code and see what they're doing. You can check how they split the data. Are they used in the good ways or bad ways? Only after you do this once, you understand what the details, what are the importance. Right? Otherwise, you will never know. There are a lot of tricks coming out there. All right. Okay? Mm-hmm. Last bit of things. Let me quickly do that. So we have illustrated all this. To me is, if you can do things manually, there are a lot of flexibilities. You can add all the extra things you like. Right? It's much easier. So the last topic is about model selection. This applies to linear regression, generalized linear models, and all these things. So you can do whatever. So we mentioned this briefly when we have p predictors, x1 all the way to xp. How do we choose them? We talked about the best subset. We talked about forward-backward selection last time. And we said in that process, using R² is not a smart idea because R² is always increasing when you include some more predictors, right? So that's something we have emphasized. The in-sample error will be going down when you include more predictors, the R-square, which is also in sample, will be going up. Right? They're not so meaningful. We said we shouldn't depend on the in-sample errors. We should at least consider these theoretical adjustments, adjusted R-square at least. And AIC, we have seen that. Last time when we do logistic regression, we say log likelihood is a measure of goodness of fit. So AIC takes that in-sample measure and the number of predictors into the same formula, just the same idea like adjusted R-square, takes the in-sample error and the number of predictors into the same formula. And yeah, there's a bunch of such things. This is AIC for linear regression. This is the AIC in general. Nothing special. Don't worry about these things. We will not use that. I put it here just to show you there's an AIC, there's a CP, and they're actually proportional to each other. So it sounds like many complicated things, but just different names. And there's a BIC. If you check Wikipedia, there's also a CIC and DIC. Yeah, this is the statisticians. They're really bored. And yeah, but all these are combinations, kind of a performance measures combining in-sample errors and model complexity into some formula, right? There's some theoretical justifications, but they're not perfect in every situation. So, let's plot these things. But you can use them for model selection. Last time we introduced a step AIC that choose your model based on AIC, right? So yeah, in this picture, AIC and CP are the same thing. So it can help you choose your model. You can switch to other different measures, AIC, VIC errors. So the smaller the better. Adjusted R-square is the larger the better, right? But they will help you, give you some idea about the good measures. But after today, we should have a much better way of doing this because we have cross-validation. We have a cross-validation, and we can use cross-validation to estimate directly the out-of-sample error. So we no longer need to depend on AIC, BIC, all these things. And this picture shows you if you are doing BIC versus cross-validation, and the conclusion may not be very different. So by doing BIC, it says you have 4 predictors. Validation set says 6. Cross-validation says 6. Right? It's the difference, but if you look at the curve, they're not super different. Right? But we know we can use cross-validation. Cross-validation is the most straightforward approximation of the out-of-sample error. So if we have that, we don't need to worry about all the theoretical kind of adjustments. But the issue is cross-validation is computationally more expensive. Think about the adjusted R-square. How much calculation do we need? And this is more expensive. Right? And especially we have so many candidate models to choose from. When we do this selection from 1 to p, we have 2 to the power of p models. Right? There are tons of models. For each model, we need to do cross-validation. That's a lot of work. So that may not be very smart. So it turns out that there's a smart way of having a hierarchical way of selecting things, taking some advantage of the structure of regression models. There are a lot of words, right? You can read that when you go home. Let me just draw the picture. Let's just make sense. So last time we said, let's start with a bunch of predictors. We have all the way to xp, right? So we said we need to decide which one to include in our model, which one not to include in our model. We introduced several heuristics: forward selection, backward selection, and some other things, right? But at the end of the day, the idea, let me just quickly repeat the idea, right? Forward selection says, let's start with a model 0, which has no predictor in it. Let's start from an empty model. Then we think about which one to include, right? We said we are comparing p different models. because we have P candidates to include into our model. And after we have a decision, we say we choose X2, we move on to the model M1. And M1 here stands for the best model with one predictor. Because we have been comparing P different candidates, we have decided including X2 is the best one. So I'm using M1 to indicate the best model within this subgroups with only one predictor. Right? There are P such models. I have chosen one. Then you consider the P minus 1 candidates. You choose your M2. X2 stays there. You may choose X3, right? And you go on in a forward way, adding one predictor a time. And we also said you can do that from backwards, going all the way from MP. That's the full model with everybody in it. And in the backward model, we say, let's evaluate this model and see which predictor is not significant. So we Q1 there, right? So you may Q1 there and move upwards. And then you go up, right? And today we are going to introduce a more exhaustive version, the so-called best subset. And you'll see the point very soon, but let me introduce the idea. The best subset says at each stage, I don't want to rely on these heuristics. So this moving from M1 to M2 is a big heuristic because since I have already chosen X2 in the previous level, I cannot take it out. I can only choose to add one more. So X2 stays there forever. I can only add. And going here from upwards, you can only delete. You cannot regret. Right? In some sense, you cannot take back your decisions in the later stage. But best subset says I don't want to do that. I'm going to think about the best in all possible combinations. So in the first level, I'm choosing P predictors. I'm choosing 0 from the P predictors. So that's M0. Right? I don't have many options. There's only one. Next level, I'm thinking about I have all the P candidates. I'm choosing 1. There's still not so many. Right? So say, given I have the constraints, given I have decided I want to have one predictor in my model, which one shall I choose? So there are P possible candidates. Right? Next level, I'm choosing 2 out of P. What's that? P times P minus 1. Right? So at each stage, I'm choosing the best possible subset. Right? Among all the models with 2 predictors, these are all the models with 2 predictors. I'm choosing the best. Right? You can see this is getting crazy. Right? But towards the end, is getting back. P choose P is 1. P choose P minus 1 is P. Right? So this is crazy. But the beautiful observation of this whole thing is there are many models I'm comparing with, but these models all belong to the family of having 2 predictors. Right? They all have 2 predictors. That's my initial constraint. I want to have 2. Since they all have 2 predictors, they have the same number of predictors, 2. They have the same model complexity. So they have the same out-of-sample performance in some sense. I don't really worry about this one is going to overfit, but this one doesn't. So I don't worry about that because they have the same measure of complexity. So I don't need to worry about out-of-sample performance because they all have the same out-of-sample performance. All that I need to worry about is in-sample. So I can choose among this big group by in-sample measures, R squared. Right? So that's the first part. So we have the within group we can do R square RSS. That should be quick, right? That should be quick if you don't have a huge data set. There are many models, but that should be quick. If you cannot afford doing that, you can go back and doing forward and backward. That's much smaller. But the same idea, things in the same group having the same number of predictors, so you don't need to worry about out of sample, right? Then you go through each group from M0 all the way to MP. The task is I'm going to choose a champion in each of the groups. I'm going to have P plus 1 champions, right? This is easy by RSS. For each group, I can find a champion. So I'm going to cross-group comparison. How do we do that? I have P plus 1 champions. How do we compare them? They have different number of predictors, and they have different out-of-sample performance, and we cannot easily just make that conclusion. So, cross-validation. It's just P plus 1 models. That's not a lot, right? So we can run a cross-validation, compare all these P plus 1 guys. We get the P plus 1 errors. CD error. We choose the one with the smallest cross-validation error. So that's supposed to be the one with the smallest out-of-sample error. Okay? So this is a hierarchical structure, simplify the stuff a lot. So there are a huge number of combinations, but all these are easily killed by within-group competition. And all that I need to worry about are these P plus 1 champions. I need to compare these P plus 1 champions by cross-validation. Right? That's P plus 1 cross-validation. So that's the whole idea. And now you might think, how do I implement this? I need to enumerate all these things and compare all these number of models, compare their R squares, all these things. So the beauty is all the way up to the CV part, you can use one line to solve that. One line of code doing the whole thing, this part. It will just give you P plus 1 champions in one line of code. Your job is to run a cross-validation to compare this P plus 1 champions. Okay? Are we good? Let me show you the code. That's linear model selection. We need to switch to another data set just because the auto data set doesn't have many columns. So it's a trivial selection problem. So we need to switch to the another one. This is the baseball data set in the book. This so-called hitters. So this is a baseball player. Each data point describes a baseball player, and the critical variable is salary. We're going to use all the other variables to predict the salary of the baseball player. The other variables are pretty much attributes and the past performance. How many runs, how many home runs, how many hits, how many assists, how many errors, all these things, right? So you're given the player's performance, and we are trying to predict the salary. Quick check of the data shows that there's some issues. 59 of the guys, they didn't report the salary. So this is a missing Y. When Y is missing, there's nothing you can do. Right? You're predicting that, and they're missing. So just delete those. So NA omit is a quick function to delete all the NAs. Here, only the salary is missing, so I'm just use a NA omit on the whole data set. Whatever is missing would be deleted. No more missing. So after that, I end up having 20 columns, within which I have one being the salary. That's my Y. I have the other 19. I'm using that as my X. So there are 260 players. Let me save the dimensions for later. We need to do cross-validation. So the magic function is in the leaps package. It's called the reg subset. Stands for subset selection for regression. There are a lot of input, but let's not worry about the input. Reg subset just can be used as an LM. Right? Remember, when we run linear regression, what did we do? Specify the data and specify the formula. That's it. Right? So here, data is the hitters. After cleaning, we have a hitters data. We are regress the salary Y versus all the other. Right? Dot means all the other variable in the data set. Right? So I'm doing that. And that's already done. Let's see what we have. Didn't run. What we have is the plot. I have just, let me do that again. So if you go all the way up, this is the output, is what's the formula, what's the function call. Then there are 19 variables, so that's your P. Actually, in this thing, you can specify which variables have to be in the model, which have to be not in the model. But I didn't specify anything, so there's a force in and force out. I didn't want to specify anything, just make your choice. So this is subset selection up to 8. 8 is the default, but we will change that later. But think about what we are doing here. So we start by M0, there's nothing to do, right? So we started with M1, the models with one predictor. So I have 19 candidates. Eventually, it chose this guy, CRBI. I don't know what's the meaning. You can check the data set. So that's the X chosen. Now we move on to M2. It chosen hits and the CRBI. And just go on and on. At each row, you have the best model in that group. These are the champions in each group. What are the final models? Okay? These are the champions. And actually, you can do a plot. Plot doesn't say anything extra, but this is a plot about all the 8 models, 8 champions we have been talking about. This is the ranking of the 8 champions. I think there you get 8 rows. Each row is one of the model. It shows you the BIC. The smaller, the better. I think that's an inverse axis. The smaller, the better. So the top one is the best model. And black and white indicating what are the variables included in each of the champions. Right. Not many new information other than the BIC. I'll show you how to find out the numbers. What's not so comfortable is this. This is only up to M8, whereas I have 19 predictors, so we can actually change that. So this is the number of variables, maximum, and Bmax. Let's make it 19. It just does the full stuff all the way to M19. All right? Nothing new, but we can force it to do all the way to the end. And if you plot, you have the 19 champions out there. So first thing is, if you're curious about model number 10, I want to know M10. I know which variables are there from that star plot, but I don't know what are the coefficients. So you can do things like this. Tell me the coefficient of model 10. So it shows you what are the variables, what are the betas, right? So internally, there are many small regression models. So you can say which one you like. And actually, in the summary of this model, reg fit full, there are many things, many things. You can check what are the hidden things? You have a R square, you have residual sum of square, you have adjusted R square, CP, that's AIC, that's BIC, all these things. So if you're lazy, you don't need to do cross-validation. You already have everything. So this is the R square plot. We have talked about R square is increasing all the time. So that's just like that. And adjusted R square. This is adjusted R square. I'm highlighting the maximum. How come it's so small? Okay. I'm highlighting the optimal point. So according to adjusted R square, the best model should be 12 or something, 11. And according to AIC, so this is AIC, the best model is 10, M10. According to BIC, the best model is 6. Right? So that already does all the model selection. Several things. Compared to step AIC, this is more exhaustive kind of search. For each level, it finds the absolute champion. But it doesn't work with logistic regression and GLM. This is linear regression only. Linear regression only, right? So if you have a GLM, step AIC is still what you have. What we have been doing is the exhaustive version. That's the best subset version. That's by default. You can specify, yeah, I want a quick solution, just do forward and backward. So you can do method. You can say method is forward. Right? There's nothing new. And if you do forward, you can check the output. If you do forward, at each stage, they will just add one variable, like we believed. There's no deleting along the way. And if you do backwards, at each stage, they just delete one. So you can check all these things. And the quick message is, we know the exhaustive search is the best search, but they may not agree on each other. So I'm listing the models at M7. This is the best by exhaustive search. This is by forward, this by backward. They're not the same, right? Not the same. They're different variables. Here, these two are different, right? But yeah, we know the first one is the absolute best. Okay, so up to this stage,
Why are they not the same?
because they're heuristics, right? Forward and backward are just the myopic kind of a way of solving this problem quickly, not comparing every alternative. Forward, you're only adding things. Maybe up to some point, you think it's actually better to delete something and adding something else. But
You're evaluating every single model, right?
in exhaustive, yes. But in forward and backward, you are not evaluating. Mm-hmm. Yeah, and the full model is the best. So at this stage, if you are fine with AIC, BIC, you are actually done. By one line of this reg subset, you get all the champions, and also at the same time, you get their corresponding BIC, AIC. If you want to compare the champions by those, then you are done already. Okay? But I want to show you how to do that by cross-validation. Let's ignore these guys first. Right? So by doing cross-validation, I'm still having the same setup, 10-fold cross-validation. I'm doing the folds right now. Why I'm doing the folds right now? Here, remember we have 263 data points. So by splitting that into 10 groups, I have the first group having 27, the other groups have 26. Right? So that's the natural result of the better method of splitting. And I'm also creating a data frame for keeping the results. So that's the data frame. I'm going to use that to save the results. I'm keeping this is the row names, each player's name. These are the salary, the true Y. And these, they're group assignment, they're fold. Okay, K-fold CV. think about now what we are doing. This is a slightly different thing, because reg subset just give me all the champions in one shot. So all that I need to know is I need to run that once, and for each champions I need to measure their out-of-sample performance. Right? So I have a k-fold outside. And for each k-fold, I'm running the reg subset. Right? The difference is I'm using the data without the case group. Right? This is the cross-validation without the case fold. Right? That's the difference. And one run of this whole thing gives me all the 19 champions based on this data set, subset of the data. Then I'm looping over the 19 champions. For each champion P, I'm using the champion model and predict that on the case fold, on the validation fold. Then I'm saving the prediction to my result. Right, that's it. That's saving the prediction to my result. Okay? Same idea, but you will see sometimes you will need to change the order of the loops depending on the context you have. Here, because reg subsets just give you 19 models in one run. And you don't want to do the models before doing the k-fold. So whereas to do k-fold first and the model first, you need to struggle a little bit. Here, model is one run, so I do the model inside. Right. So let's run it. Predict. So everything is nice. Just one thing missing is the predict function doesn't exist. We have done predict.lm, predict.glm, and the predict for reg subset object doesn't exist. So we hope we can predict using the model on the new data, but it didn't work, so we have to write it on our own. So that's our own predict function. That we are building up our own prediction function for a reg subset object. But there's nothing special. I'm taking the reg subset object. I'm taking the new data. The only thing that is special to this problem is the reg subset output is a collection of 19 champions, 19 models in the collection. So I really need to specify which model I'm using for prediction. That's it. Inside, there's nothing special. I'm just tell me which model you're using. If you're using the 10th model, I'm going to the object, pulling in the 10th model, finding all the coefficients, using that coefficient to calculate the coefficients we multiply by the variables, and that's the prediction. Okay? So don't worry about this thing, but it's just a prediction function. I just need to specify what's the reg subset model, what's the new data, and which model I'm talking about. Which model I'm talking about. Right? Good. So it's done, and you can see the output. The output for each data point, I have the true y. I have their fold earlier. Then I have 19 different predictions by these 19 different models. I'm doing a horse race over these 19 models. Right? Every model predicts on every data point. So the next thing is to calculate the MSE for each of the 19 models. That's pretty mechanical. You can just read that later. And that's the MSE. So this is the cross-validation error after aggregating. So for each data point, I have a prediction. So I can aggregate over all the data points. For each model, I have an error. I have 19 models, so I have 19 errors. Okay? And you can compare that with the in-sample error. So that's the in-sample, what's that, MSE. That's the in-sample mean squared error versus the cross-validation mean squared error. Right? We said in-sample, you would definitely have overfitting along. Out of sample error, not so much. So it says where you should find your optimal model. And there's also a possibility to do your out of sample R square. How do we plot our R square? So that's the 2R square. We have the in sample R square from the reg subset output. We said that R square is increasing. We can also do a cross-validated version of the R square. How did we do that? Keep in mind, R square is the correlation of your true Y and your predicted Y. Right? Y and Y hat, their correlation. You take a square, that will be your R square. So we're basically measuring the 19 correlations and take a square. Right? That's it. That's also R square. That's a cross-validated R square. And at the end, we have the optimal model, the optimal model that minimizes my cross-validated mean squared error. What is the optimal? 11? 11. So where are we? So we have done all these things. Again, this is model selection. Although we have trained all these so many models, we're not going to reuse that. The only thing we take back is 11. After all these things, we realize having P being 11 is the best out of sample. Right? So the final thing, go back to the whole data set, train your model, but only pick the model with 11 predictors. That's your final model for prediction. Yeah, that's the final model for predictions. You have the variables and you have the betas. And the whole thing we have done, there's an alternative way you can do step AIC. One line of code. They're different, right? Step AIC is using the theoretical AIC. What we're doing is cross-validation error, right? So let's just compare that with. So this is the output of step AIC. Let me put the output of. Are they the same? Roughly. So this is the model of output of step AIC. This is the model of our cross-validated best subset. Right. And yeah, you can do your comparison. But it may not be, yeah, so in practice, you may not want to do this, right? Having a step AIC, just one line of code, you get everything. But the idea is there, right? I think this is a pretty smart thing. And next week, after the exam, we're talking about regularization. That's built up on this idea. We have a much better way of doing model selection. Again, based on cross-validation. But in the next round, we are going to combine the two things together. Here, we are doing two things separately. How do we decide how many predictors are there? Then, given I decided how much predictors, what should be the betas? Next time, we have the lasso model. Combine the two things together. Whenever lasso model believes, hey, x2 shouldn't be in your model, it just sets the beta to be 0. Right? Think about, we are manually separating the two things, finding the betas and finding the number of predictors. Actually, they can be combined in a nice framework. And later we'll talk about that. So that's going to be the replacement for this thing. Yeah, nobody uses this in practice. Huh? So we have a lasso. We have a lasso. Yeah. But the idea is built up, right? You have to reach to this level, then you realize what's the missing part and how to build on top of that. Right? Okay, let's stop here. And the homework for today is the midterm exam from last year. I have already posted. So next week is a break. So you have 1 week of time to do the homework. It's still grouped. Just treat that as a regular homework. It's still group based. And submit your submission next Thursday, by the end of the next Thursday. Then I will post the solution next Friday. So we're doing the test next Friday. So you still have 1 week digesting that solution, all these things. But the coverage will be up to this point. up to this point. Okay? Good. And yeah, and in 2 weeks, we are doing the test. It's in class, at the same time, same classroom. Just bring your laptop. Make sure you have enough power, all the packages installed. Yeah. Don't come to the classroom and install your R. Make sure everything is working. Okay? Yeah, there was a question on how much time there will be for the exam. After the exam, you will learn this model. So we're using that model for timing the exam. So the rule is the first 100 minutes will be free. So you have a free 100 minutes. Then there's no deadline. You can take whatever amount of time you like. Every extra 5 minutes you take, there will be a cost of 1 point or something like that. So you can decide when to stop. Stop early, there's no bonus, right? The first 100 minutes is free. So you can make a decision when to stop and when to submit. Submission is based on the system time, right? On IVLE, there's a system submission time. If you submit multiple copies, I'll take the last copy, right? Okay.